Welcome back, and we're going to review some of the calculations that we've seen with pH and pOH and look at some new applications of these calculations. So you'll remember from SL that we have been given the Henderson-Hasselbalch equation. The pH is equal to the negative log to the base 10 of the concentration of H3O+. And if we rearrange that logarithm, then we are given the fact that the H3O+ concentration is equal to 10 to the negative pH. These are the equations that we're going to center around today. We also know that the ionization constant of water is given as Kw. Kw can be written as the expression the concentration of H3O+ is multiplied by the concentration of OH-. This applies to both pure water and aqueous solutions and is referred to as the ionic product. And we've actually already looked at it a bit in SL, and it's not too much more that we're going to consider in HL. Essentially, the ionic product is telling us that at 25 degrees, the concentration of both H3O+ and OH- is 10 to the negative 7 moles per decimeter cubed, and the value of Kw at 25 degrees C can be calculated using this expression. It is important that the temperature is specified because this is actually an equilibrium expression. So in acidic solutions, H3O+ ions are formed by the reaction of the acid with water, as well as the self-ionization of water molecules. So the concentration of H3O+ will be greater than 10 to the negative 7 at 25 degrees C. And conversely, the concentration of OH- will be less than 10 to the negative 7. So in pure water, we can say that the H3O+ concentration is equal to OH- and therefore is equal 10 to the negative 7 moles per decimeter cubed. In acidic conditions, the concentration will be greater than 10 to the negative 7 molar, and the OH- concentration will be less, and conversely, in basic solutions, the concentration of H3O+ will be less than 10 to the negative 7 molar, and the concentration of OH- will be greater. Because these are an equilibrium system, temperature can affect Kw, remembering that temperature is the only thing that can affect the size of an equilibrium constant. If we look at the self-ionization of water, two water molecules forming H3O+ and OH- at equilibrium, it is an endothermic process. So at 25 degrees C, it has this value, but if we change temperature, we will change the position of equilibrium and the value of K. If we increase temperature above 25 degrees, it is an endothermic reaction, so according to Le Chatelier's principle, it will favor the forward reaction, and we will increase the ionization of the water. This means that Kw will increase, and the pH will decrease because we have increased the amount of H3O+ in solution. The catch with this, though, is that the solution will still be neutral. So we will have lowered the pH of the water, but the concentration of H3O+ and OH- will still be equal. The solution will still be neutral. If we decrease the temperature below 25 degrees, it favors the back reaction. There is therefore a decrease in the concentration of H3O+ as well as OH-, and the Kw will decrease in size, resulting in an increase in pH. This follows that because we have decreased the concentration of H3O+ and pH is only a measure of H3O+, then we will see a increase in the pH. Again, the pH has changed, but the solution still has equal amounts of H3O+ and OH-, so the solution is neutral. So we can see that what this means is that the temperature will have an effect on pH. As we increase the temperature, we will see a steady decrease in the pH of the solution. In fact, from 0 to 100 degrees, we see the pH change by almost 2 complete units, from 7.47 to 5.26 in pure water. The important thing here being it is pure water, so the pH is changing, but it is still a neutral solution. So the use of pH has a specific mathematical meaning. That is, that the letter P in front of the symbol is simply saying, take the negative log to base 10 of what follows. So we can see this in many variations in our studies of acids and bases, that being pH is the negative log to base 10 of the concentration of H+, while pH is negative log to base 10 of the concentration of OH-. We are now also going to start seeing pKw and pKa. These, just as the ones before, are saying take the negative log to base 10 of what follows. So the pKw is the negative log to base 10 of Kw, the ionization constant of water. And pKa is the negative log to base 10 of Ka, which is the ionization constant of a weak acid. These relationships can also be used to simplify pH calculations, remembering that pKw is equal to pH plus pOH, which is equal to 14. And we've seen this written in a more simplified version already. So this reviews our equations that we've already seen for the calculation of pH using both H plus and OH-, remembering here that Kw stands for the ionization constant of water, which is 1 times 10 to the negative 14 at 25 degrees C. If they're expecting you to use Kw in calculations at non-25 degrees temperatures, remembering we just talked about the effective temperature, they will need to provide you with a different value for Kw in the question. So just a reminder of how to do some of these calculations. We're asked to determine the pH of the following solutions, and we have been given hydroxide calculations. So for A, we need to remember that the concentration of hydroxide is going to equal to the concentration of sodium hydroxide. But to work out the pH, we're going to need the concentration of H3O+. The equation that links the concentration of H3O+ is going to be Kw divided by the concentration of OH-. So we can then add in 1 times 10 to the negative 14 divided by 3.34 times 10 to the negative 5. Plug that into our calculator and we will get the concentration of H3O+. So 1 times 10 to the negative 14, going to divide by 3.34 times 10 to the negative 5, and we get 2.99 times 10 to the negative 10, and we plug that into our negative log equation, and we will get a pH of pH is going to equal 9.52. The solution for B will be much the same, but don't forget that with magnesium hydroxide there are 2 hydroxides. So for B, your equation is going to be that the concentration of OH- is going to equal 2 times the concentration of MgOH2, because it will release 2 hydroxides into solution. If we go through those calculations, we will be able to see that for the magnesium hydroxide, the pH will actually be 10.7. These solutions show you an alternative method. So I use the Kw method. You can simply find pOH, negative log to base 10 of the OH- concentration, and then subtract that from 14. Either way, you will get the correct answer, so you won't be penalized depending on whichever way you feel most comfortable to use. So that's our quick review of calculations and the temperature effect on Kw, and I'll see you in our next video.